Solution equilibrium, lesson 6, calculating the solubility product constant, also known as KSP. This goes along with the SE6 assignment. Yesterday, you used the green sheet to look up the KSP value for given salts. Today, you're learning where those numbers come from. Before we learn those calculations, it is important to know that the temperature of the water will determine how much of a particular salt will be dissolved. This chart outlines the amount of a specific salt that can be dissolved in water of different temperatures. Notice that the amount of KCl that can be dissolved in water increases as the temperature of the water increases. So the KSP value for KCl becomes larger as the temperature of the water increases. And that's true of most salts. The warmer the temperature of the water, the more salt you're able to dissolve. Although that is not always the case. Note that as the water gets warmer and warmer, less and less Ce2SO43 can be dissolved. So the KSP value gets smaller as the water is warmed for this particular salt. The KSP values on the green sheet are for water at 25 degrees Celsius. If the water is at a temperature other than 25 degrees Celsius, the values on the green sheet could not be used. We would have to find the correct value for that salt being dissolved at that temperature on a different data table. Typically, there's a giant book that you can look through to find the different KSP values for different salts at different temperatures. The values you calculate should be close to those found on the green sheet. But all the green sheet values identify the amount of solid that can be dissolved in water when the water is at 25 degrees Celsius. So don't be surprised if your answers are slightly off from the green sheet values. So when you calculate these, the answers you should get should be very close to what we find on the green sheet. The solubility constant, KSP, tells us how many ions can exist in solution before it becomes saturated and the ions begin to precipitate. So it tells us how much we can dissolve before that water cannot dissolve anymore. And at which point, if we continue to add a salt, it won't dissolve. It will just fall to the bottom as a precipitate. KSP constants can be determined by slowly adding a solid to a specific volume of water until the water cannot dissolve any more of that solid. So if I wanted to find the KSP value for a particular salt, I would measure out some distilled water and I would start adding that salt a little bit at a time. And I would continue to stir that salt in until the water couldn't hold any more of that salt. That is when I know it has reached the maximum dissolvable amount. I have dissolved the maximum amount of solid that water can hold. Example 1. At 20 degrees Celsius, 0.00416 moles of lead-2 fluoride can be dissolved in 2.0 liters of water before it becomes saturated with lead-2 and fluoride ions. From this information, determine the KSP value for PbF₂. Now, with all these questions, we always want to write the balanced decomp equation for the potential solid that would form, which is lead-2 fluoride. So lead-2 fluoride is in equilibrium with lead-2 ion and 2 fluoride ions. Now that we have the balanced decomp, we make our KSP expression. So KSP equals the lead-2 ion concentration multiplied by the fluoride ion concentration squared. Now, we're looking for KSP, so we can't take the number off the green sheet. We have to solve for KSP. And we know that KSP is equal to the lead-2 ion concentration multiplied by the fluoride ion concentration squared. We're going to have to find these numbers to find KSP. Well, in the question, we see we are given the moles of lead-2 fluoride that can be dissolved in 2 liters of water. And if I've got moles and liters, well, moles divided by liters is molarity. So I can find the concentration of PbF₂ given the information in the question. So moles divided by liters, that tells me that the concentration of PbF₂ is 2.08 times 10 to the negative 3 molar. We know from the balanced decomp that 1 PbF₂ makes 1 Pb2 plus ion. So if the PbF₂ concentration is 2.08 times 10 to the negative 3, the Pb2 plus ion concentration is the exact same. And for every PbF₂ dissolved in water, 2 fluorides are formed. So that means that the fluoride ion concentration has to be double that amount. So now that we know the concentration of Pb2 plus, and we know the concentration of F minus, we can substitute those into our KSP expression. We run it through our calculator, and we have a KSP value of 3.6 times 10 to the negative 8 from the information given to us in this question. Example 2, calculate the solubility constant for magnesium hydroxide if 5.4 times 10 to the negative 4 molar is the strongest solution that can be made at 25 degrees Celsius. So we do the same thing. We start with our balanced decomp reaction. Magnesium hydroxide breaks up into 1 magnesium ion and 2 hydroxide ions. From this, we make our KSP expression. KSP equals magnesium ion concentration multiplied by the hydroxide ion concentration squared. To solve for KSP, we need to know the concentration of magnesium, and we need to know the concentration of hydroxide ions. So, well, what do we have in the question? We are told that the magnesium hydroxide concentration is 5.4 times 10 to the negative 4 molar. So we know the concentration of magnesium hydroxide. And looking at our balanced decomp, if magnesium hydroxide concentration is 5.4 times 10 to the negative 4, then magnesium ion concentration is the same, and the hydroxide ion concentration is double that amount, which I know it's not proper scientific notation, but I wrote it as 10.8 times 10 to the negative 4, just doubling that 5.4. I can substitute that then into my KSP expression, run it through my calculator, and I have a KSP value for magnesium hydroxide of 6.3 times 10 to the negative 10. Now this last example is what your quiz will look like, or a test question will look like, because it's a practical question. Because like we said, in order to determine the KSP value, we would need a given amount of water, and we would have to dissolve a certain amount of solid into that water until that water could not dissolve any more solid. So calculate the solubility constant for a calcium iodate if 109.6 milligrams of calcium iodate can be dissolved in 50 milliliters of water at 25 degrees Celsius before that solution becomes saturated. Again, we start off with our balanced decomp equation. Calcium iodate breaks up into calcium ion and 2 iodate ions. From this, we make our KSP expression. So KSP is the calcium ion concentration multiplied by the iodate ion concentration squared. We have to find the calcium and iodate concentrations in order to solve for the KSP. Now, how will we find those? Well, we've got milligrams given to us, and we have milliliters. Well, if we've got milligrams, we're going to have to switch that to grams. So to switch it from milligrams to grams, grams are bigger, my number gets smaller. Milli means the decimal moves 3 places, so I have 0.1096 grams of calcium iodate, which I will then switch to moles. Now that I have moles of calcium iodate, if I divide that by liters, that will give me the concentration of calcium iodate. So moles of calcium iodate divided by the number of liters, and that tells me the concentration of calcium iodate that I can reach, maximum concentration I was able to dissolve, was 5.622 times 10 to the negative 3 molar. So if that's the concentration of the calcium iodate, the calcium ion concentration is the exact same, and the iodate concentration in our balanced equation tells us the iodate concentration has to be doubled, so that gives us 11.244 times 10 to the negative 3. I now go back to my KSP expression, substitute in my concentration for calcium, my concentration for iodate, run it through my calculator, and the maximum dissolvable amount, the KSP value for calcium iodate is 7.11 times 10 to the negative 7. Yes, 7-Eleven. Get some drinks. Yeah. And that's it. That's the end of the lesson. You guys are good to work on the SE6 assignment.